Hi guys, this is Karthik Arora. In this video, I'm going to discuss the essence of binary search. I'm going to discuss what is the generic idea behind binary search, what are the kind of places in which we can actually apply binary search. So I'm not going to just discuss that we are given a sorted array, we have to find a particular element. That is not the goal of the video. The goal of the video is to basically introduce you to binary search in a mathematical way, so that not just to some of the possibilities, you could actually apply binary search in real world and to as many problems wherever it is applicable. So I'll be discussing the generic ideas, what are the kind of places in which you could apply binary search, and some common examples of of problems being asked in coding interviews and even in competitive programming platforms. So even if you already know binary search, I think this will be a video in which you will be able to gain something new. So watch till the end. Hopefully you are going to like it, and let's get started. So let us start with the problem statement. And the problem statement is that you're given with a function f. You would like to find the point x such that f of x equals to y. So you want to find at what value of x does fx become equal to y. And you can say that f is a function from real numbers to real numbers. Now this is the goal of the video currently. Now let us make this problem a little bit more interesting and add another constraint to f. So the graph for f looks something like this. Okay, so this is the graph for f, and the essence of this graph is that as x increases, f of x also increases. Either it does not increase and stays the same, or it increases but it never decreases with the increase in x. Let's say that I know that I wanted to find the point x1 so that fx1 is equals to y1, right? This is what I want to find. Now assume that you know that x1 lies in the range low to high. Okay, let's make this kind of assumption that we know that x1 lies in a particular range. So maybe we know that x1 lies somewhere in this region, something like that. Okay, you already know that x1 is going to be somewhere in this region. Actually it has to be minus infinity to plus infinity, but normally in coding problems you could take minus 10 power 9 to 10 power 9, and that can be considered as minus infinity to infinity. Or if you have a tighter bound, it's even better. Now if I were to do a linear search on this particular value to find x1, what I could do is I could try out every value in this particular range, assuming that this is a discrete range instead of continuous range. Then I could simply try out each and every value and I will definitely find my x1. And the time taken to find it will be big O of high minus low, or the range size, which is not bad unless the range is very large. Like it could be up to 10 power 9 as we discussed. So in that case, this is not at all good. And here comes the idea of binary search. Instead of solving this particular problem in big O of r, binary search will be able to solve this in big O of log times the range. And how will it do that? So this is the idea behind binary search, and this is not the only graph on which you could apply binary search. I will discuss variants of graphs on which you could actually apply it, and I will also discuss problems on which this technique is being applied. So assuming that you knew that answer lies somewhere in this range, what you could do is you could try the mid value. Okay, you could say, okay, what is the value of f at mid, and let's define mid to be low plus high by 2. Okay, then you could find out what is the value of f at mid, and if f at mid equals to y1, then you are done, because then mid equals to x1 and work is done. Otherwise, the thing is that if f of mid is greater than y1, so graphically it will look something like this. This is mid, this is f of mid, and if this particular value f of mid is greater than y1, that means y1 was somewhere below, then this means that you can safely assume that no value in this region is valid. since as you go to the right of mid, your f of mid will only increase. Basically, f of x will only go upwards. However, you want your f of x to go downwards, isn't it? Because y1 is less than f of mid, so you want it to go downwards. And you can safely assume that your search range reduces to this region. And just by doing this single check, you have eliminated this right portion, given that f of mid was greater than y1. But consider the other case, that f of mid was less than y1, and let's say that your y1 is somewhere here. Okay, then this means that going to the leftwards will only decrease the value of fx, and therefore since you want it to be equal to y1, you have to go rightwards because you want to increase it upwards. So you have eliminated the left portion. So just by doing one check, either you have found your answer or you have eliminated exactly half of the search range, isn't it? And here is the idea. So after one check, your range from R becomes R by 2 because one of the portion, either left portion or right portion, gets eliminated. And in the remaining area, you can again apply the same idea recursively, and you can say, okay, you tried for this region and you found out this region was useless, so you are left with this particular region. So let's consider this guy, and I will try to find take the middle of this point and again find the value. Depending upon if it is equal, then I'm done. If it is less than or greater than, either left portion or right portion gets eliminated. So basically here my range was R. After one check, my range became R by 2. After one more check, either this portion or this portion gets eliminated. That is exactly R by 4 of the portion will get eliminated. So after one more check, my range will become equal to R by 4, my search range. And you can continuously keep doing this till your range is so small that you have already found the answer, because assuming that we are only considering integer points x, then you will always reach a point when low equals to high. That means your range is exactly one element, and that one element has to be your answer, and otherwise the answer does not exist. So let's analyze the complexity here. So initially you started off with a range R. After one step you had a range R by 2. Then after one more step R by 4. And finally you will reach a point when this particular range is exactly of one element. Okay, so the range the search range is exactly one element. So assume that after k steps you will reach, so that search range is exactly one element, and this means that 2 power k equals to R because this is one element. So you can say R equal to 2 power k. You want to find after how many steps will you reach this point. So you can take log both sides, log base 2, and you will get k equals to the log of R, and that is the time complexity for binary search. Now let's relate this simple idea to some actual applicable problems. Okay, so we had this particular graph. Now given a sorted array, you can assume that if you plot this array with the indices, the value of the element versus the index. So if I plot the index here and the value at index here, for a sorted array it will always be increasing graph, right? If it is sorted in increasing order, then it will be an increasing graph. And I could apply binary search on the index to find at what index do I have the value, maybe x, right? So instead of doing a big O of n time linear search, I could go for a big O of log n time binary search. So that's cool. This we all knew. What's new? So let's try this one out. You're given an integer n and you would like to find the square root of n. So you given n, find root n. And of course you cannot use the power function or sqrt function because I know you all know that they exist, but we don't want to use them. So I will assume that, okay, I wanted to find the square root of n. Of course n has to be a real positive integer or a real number that is positive at least. And let's say that n is here, this is my number line, this is 0, and I know that my answer lies somewhere here. Okay, so if x is my answer, then it lies somewhere in this range from 0 to n. That is definite. I could set have tighter bounds, but I am sure it has to be somewhere here. So what I can do to find x is that I could use binary search again. Here is what you could do. Assuming this to be your low, high, the starting of the range, the ending of the range where x lies, try the middle point. So is this the correct answer? You will say, okay, trying mid. Is mid into mid equal to n? If it is, then you have found it. Okay, because then the mid squared equal to n, and of course that is what you wanted to find, a number whose square is n. If that's true, then you have found it. Otherwise, if mid into mid is greater than n, then that means any value to the right of mid, which if selected, will give you an answer that is even greater than mid square, right? That means that will obviously be greater than n, so you could safely discard this region, and you can assume that your square root lies somewhere in this range from 0 to mid minus 1. This will work even for numbers that are not perfect squares, and this is in fact how it is implemented in our computers. However, let's just assume that our number is a perfect square. Otherwise also it will work. However, then you will get the final answer that you will get will not be the exact square, but it will be very close to the actual answer. Like as the higher number of iterations you do of this binary search, the closer you get to the answer. So you can say that after doing this particular thing 30 times, you can get an answer that is close to the real answer of the accuracy of 10 power 9. So if your actual answer is x, if you do this particular thing 30 times, you will get this close to your answer, the actual square root, given that n is not a perfect square. Anyway, so let's just ignore this error thing right now. Assuming that our n is a perfect square, then we know that my search range should be 0 to mid minus 1, because any guy here does not work. They will obviously be larger than n. Their squares are larger than n. So my search range becomes this. Now you can try the middle of this point. Let's say that the middle of this point is, again, I updated my high to be here, and now again this is mid. Assume that mid into mid equals to n, then I'm done. This is the answer. Otherwise, if mid into mid is less than n, then I could safely discard all these elements. Why is that so? Because mid into mid is less than n, then any element that is smaller than mid, the square of that number will obviously be less than n, right? So you can safely assume your answer lies in this range. And this is how we can use binary search to find the square root. And not just square root, you can use it to find cube root, fourth root, fifth root, anything. Instead of doing mid into mid, simply check mid into mid into mid, right? The thing is that simply check, if you want to find the nth root or the kth root, you could do a binary search. You could find what is mid power k, and then compare it with the number whose root you are finding, and then you could keep applying the same idea. Alright, that's cool. Let's see on what more variants we can apply a binary search idea. So assume you have a function f and you have an integer x, and as x increases, f of x decreases. So the same idea of binary search can be applied here also, and instead of like checking mid and comparing it with the value you wanted, you can safely adjust whether you want to go to the right or left, and if a function looks something like this, even then you can apply binary search. So these kind of functions are known as monotonic functions. So either they keep increasing or they keep decreasing as x increases. Okay, so these are known as monotonic functions, and binary search can be easily applied to a function that is monotonic. So let's take a dumb example for this. Let's say you want to find out what is the maximum money that you can ask your parents to go out, and you say, you ask your mother maybe, can I have 10,000? And she says no. Then you ask, can I have 5,000? She says no again. Can I have 2.5 thousand, 2,500? She says no. Can I have 1250? Or let's say that she said yes here. Okay, she said okay, you can have 2,500 for your birthday party. So you were very happy, but you wanted to bargain more. So can I have 3,000, like the middle point here? Can I have this much? And she'll say yes or no. and this might be a good strategy to bargain, and the function will look something like this. It will be a yes for smaller values of money, and it will be a definite no for larger values of money. So for 10,000 it will be no, and for smaller values it will keep on becoming yes. So that is the idea. Like, this kind of functions can also be used, applied binary search on. So is that all, or is there more? So let's think about these kind of functions. A function that first of all decreases and then increases. So it does not need to be a linear function. It could be a parabola, it could be anything. So the idea is that it decreases first and then it increases, and all you are need to find, the thing that you need to find out is the minima of this function. So you want to find out the point x where f of x is minimum. This is what you want to find out. And how can we find that? Of course, binary search. And how do we apply binary search to find this particular point? So here is the thing. First of all, you know that your answer lies somewhere in the range low to high. Okay, this is your function. Sorry for the bad drawing, but yeah, let's just focus on the essence of binary search here. So you want to find this point. You know that it lies somewhere in this range from here to here. And you try out a random point and you evaluate the value. How do you know whether the answer lies to the left or right? You evaluate this value here, and now either your actual answer lies to the left or right. How do you know that? And let's not evaluate it here, let's actually evaluate it at the midpoint maybe. So let's say I evaluate it here. How do I know should I go left or right? So the idea is quite simple. We know that our function has two parts, an increasing part, a decreasing part followed by the actual minima point, the one I want to find out, and then an increasing part. I know my function looks something like this. First there's a decreasing part, then my minima, and then the increasing part. So if this particular point is the minima, then to the left of it and to the right of it, both the elements are going to be greater than this point. And for this guy, this is not true. The left one is smaller, the right one is greater. So this is definitely not my minima, because for the minima, the situation is something like this. It is at a valley, right? So both left point and right point are at a higher point than it. So if you evaluate f of minima minus 1 and f of minima plus 1, you're going to get values that are greater than f of minima. So this could be an idea that, okay, this is not the minima, but still, is my answer to the left or to the right? So since you want to move in the direction of the minima, you know that to the right, my actual function is increasing, right? You can simply evaluate at this point f of mid, and you can evaluate at f of mid plus 1. If your function is increasing in the right side, that means f of mid plus 1 is greater than f of mid, then you need to move to the left side, because you want to go to the valley, right? And if you were, let's say, somewhere here, then you could have evaluated f of mid plus 1 and f of mid minus 1, and you could have seen that, okay, mid plus 1 gives me a better hope, and it basically, it's taking me to smaller values, it's taking me to the actual valley, so I should move to the right point, rightwards. So just by knowing this gradient, right, the gradient, wherever the gradient is decreasing or wherever you're about to go down, that is the point that you should keep your search range to. So if you checked this point, after this point you should update that, okay, my answer lies somewhere in this range, and all these elements will simply get eliminated, and you can find this minima. And this is nothing but the problem being very commonly asked at companies like Microsoft: find the pivot element. That is nothing but exactly this function, and you are supposed to find out the minima. So yeah, one more thing that you can do is you could have functions like this, and you could find this particular point, the maxima. And I guess I don't need to actually show you how you can do it, but it's quite easy. Have a search range, try a point, and then keep adjusting the range, and this time look at the gradient where it is going upwards, and take that range to be your actual new search range. And guys, that's it. Now one last thing that I want to discuss is that till now I just assumed that evaluating f of x is very simple and it can be done in big O of one time. it's not always true. Evaluating the function at a particular value is not always so easy, and sometimes it is costly, sometimes it's not even feasible. So for your practice, I want to suggest a very nice problem. It is from SPOJ, aggressive cows. It uses the binary search idea. All you have to think is, how do you evaluate f of x, basically the function at a particular value. You have to come up with an algorithm that uses binary search, and you have to find a way how you can evaluate your function at a particular point. And this is a really nice problem to show you the power of binary search. And guys, I hope this particular video was helpful to you, and you will definitely like, share and subscribe the channel. Thanks for watching.